Welcome to Lesson 4A, Isentropic Converging Nozzle Example. In this lesson, we'll use what we've learned so far about converging nozzles to do an example problem. We'll do both a choked and an unchoked case, and I'll show you how to calculate and plot Mach number and pressure along the nozzle. Here's the problem setup. We have our typical tank with stagnation properties. I chose this as our x equals 0 value, calling it the inlet, and we have an outlet with a known area. We're given the back pressure, PB, the stagnation values, and cross-sectional area A as a function of x, the axial distance from the inlet to the exit. For isentropic flow, we'll calculate and plot Mach number and pressure as functions of x, and then we'll repeat for a higher value of back pressure. We make the usual assumptions and approximations: ideal gas and its air, steady, isentropic, adiabatic, and one-dimensional. Here's our area ratio versus Mach number relationship and our equations for isentropic flow. The first thing is to figure out if this flow is choked. To do that, we calculate PB over P naught and plug in our known values to get 0.2273. This is lower, in fact much lower, than P star over P naught, which is about 0.5283 for air. Therefore it is choked. And since it is choked, A star is the actual exit area. Now use our area ratio versus Mach number relationship at each x location, and we solve implicitly using whatever technique you desire to get Mach number as a function of x. One cautionary note here: there are two roots of m at a given area ratio, a subsonic and a supersonic one. Since this is a converging nozzle, we can't go supersonic, so we must use the subsonic root. So make sure you pick the correct one. Once we have m at each x, we use the isentropic pressure relationship to calculate the pressure at each x location. Namely, using ratios, we set P equal P over P naught times P naught, and our isentropic relationship at a known m can be used to calculate pressure. I used Excel since there are lots of repeating calculations, and then it's easy to plot as well. One note here: at the exit plane, since the flow is choked, AE equal A star, or AE over A star, is 1. Thus PE equal P star, and again using clever ratios, this is P naught times P star over P naught, and using this equation with Mach number equal 1 reduces to gamma plus 1 over 2, and then the same exponent, and we can plug in our P naught and 1.4 for gamma, which gives us PE equal 116.222 kPa, and ME, the Mach number at the exit plane, must be 1, since the flow is choked. As you'll see when I show the plots and the tables from Excel, these values agree with the Excel results. So that's just a nice check of our results. Here are my results from Excel. I don't show all the columns here. I actually used Newton's method to find my m at a given area ratio. And note that this area is A star, which is also the exit area. And as I said above, at A over A star of 1, the Mach number is 1, and our pressure at the exit is 116.222 kPa. This is PE, and it's also P star, and this is the exit Mach number. I also point out that this exit pressure is not the same as PB, the back pressure, which was 50 kPa. But as long as PB is less than this value, P star, nothing in our table would change because the flow is choked. Here's a plot of Mach number. At the inlet, the Mach number is about 0.35, and then it grows toward 1, being exactly 1 at the exit. I also plot pressure, which starts slightly above 200 kPa and falls to P star at the exit. Now let's repeat for PB equal 180 kPa. You can easily see that this flow is unchoked, since this new value of PB is bigger than P star. Thus this flow remains subsonic everywhere in the converging nozzle. The back pressure is not low enough for the flow to choke. Well, the first thing we can do is apply our isentropic equation for pressure at the exit plane, which I indicate by these subscripts E. And here, PE must equal PB since the flow is subsonic everywhere, and this flow is not choked. We plug in our values of PB or PE, P0, and gamma, and the only unknown is Mach number. So we solve this equation for ME. I get 0.54318. And you could solve this explicitly. There's no need for iteration. Now we need to calculate M and P at each X location like we did previously. But we have a problem. The exit area is no longer equal to A star since the flow is not choked. In fact, the Mach number is just a little bit above a half here. It's nowhere near 1. But we need A star to calculate M and then P at each X. I'll ask the students, how? How are we going to calculate A star?
Since both Mach number and area are known at the exit plane, the most logical thing would be to use these values and calculate A star, which would be the only unknown in the A over A star relationship.
Great idea, Jim. Let's plug in our known values of ME and the area, AE, and gamma, of course, and solve for A star from our area ratio versus Mach number equation. I'll write that out here using subscript E for the area and subscript E for the Mach number. This equation is explicit since we know ME, so we can get AE over A star. Then, and I'll call this a new A star, is equal to AE over A star. Again, always using ratios to help us find these things. We know AE from the table, and from the above equation, we know AE over A star, the denominator, and thus we calculate the new A star to be 0.013952 meters squared. One comment here. This new A star is less than the original A star, which was equal to the exit area, which from the table was 0.3 square meters. In fact, the new A star is much smaller than the old one. I'll give a physical explanation for this. Let's sketch the actual nozzle shape, where the exit plane was the original A star. But now imagine an extension to this nozzle, where we have a new A star. If we added an extension like this, the Mach number would be 1 at this new A star. But this is just an imaginary extension. This new A star does not exist anywhere in the flow. Another way of saying this is that this new area of our imaginary extension would be the new A star if PB were small enough, namely less than P star. But this area is our actual exit area, which is bigger than the new A star. And this is the location where P equal the back pressure, which is 180 kPa. And the pressure at the end of our imaginary extension would be P star, since this is the area required to choke this flow. Remember something I said in a previous lesson, and that is that we can use A star as a variable in a given problem even if A star doesn't actually exist anywhere in the flow. Since our nozzle is cut off here, we know the pressure there at our actual exit plane, so we can call this PE, and the Mach number at the actual exit plane was calculated previously, so now we have everything we need since we have our new A star. So now we use this new A star to repeat our calculations. Again, I used Excel, and all I had to do was copy and paste my previous cells, but use a different A star. Here are my results for the non-choked or unchoked case. This is the actual exit, remember at x equal 0.3, and our actual pressure is the back pressure, 180 kPa. I added a row for the hypothetical extension, where this is the new A star that I used to calculate A over A star. You can see that that's 1 at the exit of the hypothetical extension, and the Mach number is also 1, and this value is our P star. So we plot these values, everything above this last row, since this is just a hypothetical extension. My legend shows the value of the exit pressure, The 116.222 is the red curve that we saw previously, starting from 0.35 and going to 1. This dashed green curve is for the higher back pressure, which is also equal to the exit pressure. The Mach number turns out to be lower at the inlet and reaches only 0.543 at the actual exit plane. Similarly for pressure, the red curve is the choked case, and this green curve is the unchoked case. And I'll also label the ones on this plot. One final comment is that this P star is the same P star that we had for the choked case, even though it doesn't exist in this actual nozzle for the second case. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3. That's all there is to it.